I'd like to get into the next problem. I'm going to go through kind of an answer key roughly of my second pump application worksheet, pump selection 2, number 43, M143. So what I'd like to start out with is just do a little explanation. So I already went through the first problem in a previous little mini video. I'd like to go through the second problem, and the second problem identifies, it's saying, for the above system that we did previously, this was the pump curve for that above system for number 1. We determined that the flow rate was too low, and the service technician decided you want to use a different pump, maybe the UP grundfos UP 2699F pump, but before he decides, he wants to know how many gallons a minute he's going to get from the new pump and determine the rest of the information that's needed. So let's maybe do a little preface of this, and let's figure out how do we determine if we're too low on water. So the way I would do this is I would identify this as this. So let's say that my water coming out of my particular boiler here happens to be at 200 degrees. And as I travel to each of these two zone valves, let's call this zone valve number 1, and this would be zone valve number 2. And zone valve number 1, we might go through all of those heat emitters in that first zone, or in that zone. And that particular application maybe it comes back at 160 degrees Fahrenheit, which would be, in this case, a 40 degree Fahrenheit delta T in this example. Now zone 2 is also going to see the same 200 degree water, so you're going to have 200 here, and you're going to go through all of the heat emitters in that section, and maybe we find that that particular zone here happens to be, maybe the return temperature coming back and there happens to be about 165 degrees as an example. Now, what would that tell me? So I would see that as, we're 5 degrees difference between, the 160 and 165. We might have a slight little balancing issue, but nothing too major. So that would also mean that my common return temperature would have to be somewhere between the 160 to 165 degrees Fahrenheit, depending on the percentages or the proportions of what the flow is distributed between each of those two. But so let's just say it doesn't really matter, but let's say that the average in between the two was 162.5 degrees Fahrenheit roughly. So that doesn't matter whether it's 162, 163, or whatever it might be. Either way, it's a fairly high. So we're anywhere from about a 35 degree delta T all the way to a 40 degree delta T. All right, now, why would we be low on water flow, or what would be the problem here? So if I designed my system for assuming that we were going to have this big of a delta T, I would have had to have made sure that the heat emitters near the end of my loops, whether it's here or whether it's here, those heat emitters, I would have had to make them a little bit longer. So those are going to end up, because the water temperature in those emitters they have lower water temp, they're going to get actually less heat output out of those. Lower water temperature is always going to equal heat output is going to be less. And that is just a fact. That's the way it's going to be. And if you take a look at, what do we do about that? So what can we do differently? So if the customer at the end of this loop were saying, this room is always cold. It always seems colder than the rest of the rooms. And when you start looking at it, the ones in the front of this thing, the first of the zones, those heat emitters, those very well could have been they could have been giving them more output than what they needed, and those zones were a little bit warmer, and the emitters at the end of the loop, which we're gonna which I'll show you is right up in this area and in this area, they're not giving as much heat output. So if I saw that in the field and I identified this as saying, you know what, I tell you what, we can put a pump on that would be a little bit bigger pump or something that would be able to handle more head. But I want to be able to predict ahead of time once I identify, hey, I know what my supply to return delta T is for the systems, and I know what my flow rate is. So in the flow rate, to determine how many GPM that I have, I would simply be taking the same calculation that we normally would do. I would end up taking my BTUs per hour output that I would determine from my system and divide that by 500 times my delta T. The delta T that I would be using, this delta T here, that would actually be the difference between here and here. What's going in and out of my boiler system is what that would be. So that is my delta T between those two. So that's ultimately what I really want to do. Now, when I'm checking a system in the field, I definitely am going to be looking at this one and this one. I want to look at those two delta T's to make sure that that they're reasonable, that you don't have one that's getting way too much water flow and one that's getting very little water flow when they're all calling, and so I want to make sure I do that. So here's the deal. So right now, if we know that we have somewhere between a 35 and a 40 degree delta T is what we have. And most of the time, we might design a system, a high temp baseboard system that would give us closer to about a 20 degree delta T is more normal. All right, now nothing wrong with, you can certainly do a 35 or a 40, but if you're not designing the system for that, then those emitters on the end are going to be suffering, and so we want to bump the flow up. So there are very few situations in the field where you would ever have a situation where it would be to a disadvantage to have a little bit more water flow. In most cases, you're going to get a benefit by having more water flow simply because it lowers the delta T between the supply to return, and it provides and it offers the output, the heat emitter output out of the runs on the end, out of these last baseboard, whether it's here or here. Those emitters are going to start to get more output because they're going to actually see a higher temperature going into those baseboard, and that will give them more output, more BTU. So that's really why we would want to do that. The delta T is really the key that we are looking at. So, and that's really what you have to kind of decide in that. So design delta T's can vary a lot, but that's another lesson that we'd go through. So let me show you how to figure out that second problem then. So in the previous problem, we identified that our pump would give us approximately about 8.3 gallons a minute at about 9 feet ahead when I was using the GoPro app or the grundfos Go Remote app. And so what we're going to do is I'm going to switch it over and do that second problem using that app. Now, on the worksheet, you probably had you actually had the curve that had multiple pumps on there. However, this phone app is the app that the grundfos Go Remote app, which many of the manufacturers have this. It's just a nice, easy, fast way. Hey, is this, what's going to happen? Once you can identify your flow rate, that's going to be great. By the way, this does equal your GPM. So that's, anyways, so that formula. All right, so let's take a look at it. So I already have my Go app that I have open now. I'm going to select a heating, and I'm going to go to UP series pumps with series 100. And since I have in the question that I wanted to use a UP 2699F pump, I'm going to select the UP North America pump. And it's UP. I have several of these 2664 all the way to a UP 26120 pump. So the pump that I chose that I wanted to try using is a 2699F pump. So I wanted to see what that one's going to do. And of course, I'm going to choose a 115 volt pump in this case. All right, so that picks that up. And I'm going to go to the curve. So this will be the curve, and it's going to identify that we're going to have a maximum flow rate that this pump could do is closer to about 33 to 34 GPM and about 32 feet ahead max on the left side and the bottom. So let's go ahead. I'm going to tap that pump curve. So I just touched it, and this is what pops up. So the Q is going to be the flow rate. Now what I would do is I would use what you determine as the flow rate. So if you figured out based on your the BT's output divided by 500 times your delta T calculation, and you determine the flow rate, use that one. In my example, I'm going to go back to my original, which I felt was known, and that was going to be the 8 GPM at 8.4 feet ahead. So I'm going to punch this in. So 8 gallons a minute, and I'm going to choose the feet ahead is going to be, okay, there we go, 8.4. And that was identified in the problem. So now what this is going to do is it plotted the entire pump curve, and it identifies my head as well as the as well as the flow rate for using that 2699 pump. So I'm going to tap the pump. Whoops, I got to update that again. Don't want to tap the pump. There we go. Now I'm going to hit the X button on here, and then that brings me back, but it didn't lose my curve. So in this particular case, it is identifying for me, and I'm going to do a little screenshot on this one. Okay, and I'm going to get this one, make this one a little bit smaller, and I'll bring it back into the problem. All right, and that one's done. Save it to my photos. All right, so what do we have here? So that tells me my flow rate with that 2699F pump would jump up to about 13.4 GPM, and the head would be about 23.44 feet ahead based on their app and their calculation, which for most, of our service applications, that's more than adequate. Whatever accuracy that we can get on there, that's great. But this is a nice, super fast, easy way to do this. So let's go back to the PDF expert problem that I had identified in here. So what I'm going to do is add an additional page, and I'll do a blank page, and I'm going to identify, I'm going to insert that image that I just got done doing. And I'll do it low quality, keep the size of the document down a little bit, and there we go. So now that would really be my answer to that particular problem. Now I'm going to annotate this one here, and I'll just identify that as problem number 2. Problem number 2, when I choose that particular pump, that means my GPM is going to jump up to about 13.4 GPM. And this will be at the feet ahead, which will be 23.44 as identified. All right, so that would be how that would be done. Now the other part of the question that I asked is, well, if I've got 23.44 feet ahead with that particular pump, what does that do for me for my PSI? So the question I asked was, it said determine the new GPM and the friction of the system in both feet ahead and PSI. So I've given you the GPM, I've given you the feet ahead. Now we need to figure out the PSI. So the calculation that we're going to do here is taking the 23.44 feet of head, and our calculation is that we know that there is 1 psi for every 2.31 feet of head. So the feet of head cancel out, and so essentially I'll be taking the 23.44 and I'm going to divide that by 2.31. So that will end up giving me, and let's see if we can get this to go. All right, 23.44, divide that by 2.31, and that comes out to about 10 point, let's call it 10.1, 10.15 in that area. My problem, so that is going to equal approximately 10.15 psi. So that is the answer to problem number 2.